Hi everyone, my name is Katrina and I'm here to talk to you about persistent data structures. So we are used to ephemeral data structures. They are passed by reference and you can only hold them in one space in memory. When you modify the data structure, it destroys the old version. A persistent data structure, on the other hand, makes copies of your old versions and preserves the previous versions of itself when modified. There are two main types. One is partially persistent. These are ones where all versions are accessed, but only the most recent one is modified. The second one is fully persistent, where all versions can be both modified or accessed. So why are they useful? For one reason, they are inherently thread safe. For multi-threaded programming languages, if you have multiple threads sharing the same data structure, you wouldn't want one thread manipulation on that data structure to affect the execution of the other thread on that same data structure. And you can store the immutable data in arrays. Since the mutable data structures are stored in one place in memory, they are highly immobile. So you would have a chain of references to that data structure, whereas here you can just make a copy wherever you are in your script. Since it behaves like a variable passed by value, the variable you assign to the structure is immutable, so it's easier to read. So throughout your program, you know that that variable will hold the same value. So how can this be achieved? You can do just simple copying of the structure, but it's a waste of CPU operations and RAM storage. And most operations just modify a small portion of the structure. So a better method is to exploit the similarities between the old and the new version between them. The JavaScript library that does this is called Immutable.js, and they have it for various data structures such as stacks and queues and linked lists. Researchers have devised generic techniques to forming immutable data structures, and we will be going over how to make linked data structures persist. So before we go into linked structures, I just wanted to give an overview of the definition of a linked list. It is a finite collection of nodes, each containing a fixed number of name fields, and each field holds information or is a pointer field to another node, or holds one special value null. And access to a linked structure is provided by access pointers, which are the heads and tails, and they point to the entry nodes. So the three techniques for how an immutable linked data structure is made is fat node, path copying, and a combination of the two. The first method has all the nodes being objects and your nodes are ephemeral as in your regular data structure, but it contains the fields in the node contain all the versions of your previous values. So each node has like a version history of the value. These versions are accessed by an array, and so accessing the version takes O of one time, and it's O of one space per ephemeral update step for modifying the value. Now the drawbacks are that you need to determine ahead of time the number of versions in your node, and you need to choose the length of and that determines the length of your auxiliary array. Sorry. Okay. So the second method is path copying. So for a singly linked data structure, changes to the node are only visible to the nodes that precede the changed one. So essentially what you do is that if you want to insert a node, you make a copy of all the ancestral nodes recursively until you get to the root. And then that pointer will point to the next node in the previous data structure. And these versions are arranged by timestamp in the array. This is for a tree. We insert E, and then we copy the ancestral nodes, including the pointers, and they point to the nodes of the previous data structure as it cascades down. And again, they're assorted by timestamp in the array. So lookup time for the versions of these data structures take O of log m time for n modifications. Okay, so the third method is combination. It's kind of the same as path copying, where each version is stored by a timestamp, but each node contains the field and just a modification box that has a timestamp next to it. And it's initially empty when you first make the data structure, and it either holds a change to the node's pointer or some piece of node-specific data. Okay, so for accessing a node, you check the modification box and compare its timestamp against the access time, which is the time in the timestamp in the array of when you're accessing the version of that data structure. And if it's empty or the access time of that version is before the modification stamp, then you deal with the node normally. Else you deal with the modification box. And for modifying the node, if the modification box is empty, then you write the value there. And that new version of that data structure will point to the modification box. Otherwise, if the modification box is full, we make a new node and overwrite that value in the modification box to that new node. And we copy the ancestral nodes as we saw earlier. All right, so these were my sources to learn about persistent data structures. And I hope you found them entertaining. All right, that's it, I think.